Have you started? Okay. So the question is, what? If you wouldn't mind, just read to me the exact question. We have a production function, right?
Yeah. Suppose the production function for Q is given by QKL.
Q equals Q of KL.
Yeah. Q of KL equals K to the power of 1/2. L to the power of 1/2.
Okay. Then what's the question asking, or what's the part of the question that you're interested in?
The part of the question what I'm interested in is
Sorry to disturb you.
No, come on in. We're just filming this. Okay, go ahead.
Okay.
The part of the
how
question
do
you're
you
interested in.
find the marginal productivity.
Right, so it's asking, one of the issues was what is the marginal productivity of capital, and is it decreasing or increasing as I increase capital? In other words, how does output change as I increase capital, and so we know that output will increase as I increase capital, but will it increase at an increasing rate or a decreasing rate? Right, so I have to know what is the slope of this in K, holding L constant. So holding labor constant, how does this change in K, and does that change increase or decrease as I increase K? In other words, do I have a case where this is holding labor constant, where output is increasing in capital at an increasing rate, a constant rate would be a straight line, or a decreasing rate? Is the slope, so we know we want to compute the slope and figure out is the slope, so the slope is the first derivative, we could in fact even plot the slope. Is the slope itself increasing, decreasing, or staying constant? Okay, so I put up a tip that the derivative of Cx, the partial derivative, the derivative with respect to x of a general function Cx to the a, y to the b, where a is not equals to 0, okay? The partial derivative of this, in other words, how does this change in x as we hold y constant, a and b and c just being parameters, just simple numbers, right? And then the rule for that, or the set of rules, is that the derivative of this will be a c x to the a minus 1 y to the b. Okay, and this is basically two rules. One is that y to the b and c are both just constants. The only thing that's affected by x is the x to the a component, right? And the derivative of any constant, the derivative with respect to x of f of a, derivative with respect to x of a f of x, in other words, a constant times a function, is just equal to a times whatever the derivative is of this function. So the f of x with respect to x. So the constant just stays outside, right? It's easy to see in the linear case that that's the case. The second rule is, and this one is not so intuitive, is that the derivative with respect to x of any function of x to the power, let's say a, where a is not equals to 0, the derivative of this is just a times x to the a minus 1. Okay? As long as a is not equals to 0. Okay, combining those together, we get this rule here. I just take the things that are constant, y to the b and c, put them outside, and then I apply this rule to x to the a. Okay? Okay, so now I can go ahead and apply it to this function here. I want to know what is the slope of this function k to the 1/2 L to the 1/2 with respect to k. So the derivative with respect to k of k to the 1/2 L to the 1/2. Well, I know L to the 1/2 is just a constant here, so that just equals, I can take that outside and say L to the 1/2. And then I look at the derivative of k to the 1/2, and I use that rule we just mentioned before. The derivative of k to the 1/2, take this, put it down here, so we get 1/2 k, and then the exponent, you subtract 1 from the exponent. So we say L to the 1/2 times 1/2 k to the negative 1/2. Okay, I could rearrange that and say it's 1/2 L to the 1/2, and then k to the negative 1/2 is just 1 over k to the 1/2, or 1 over basically the square root of k. So I can say 1/2 times L to the 1/2 k to the 1/2. right? Because it's negative 1/2, so it goes in the denominator, okay? So now I have I know the slope of this, and I know how the slope of this change, I know the slope of this as a function of L and K, okay? So first of all, is this term positive or negative for positive values of L and K? So half, oh, sorry, you don't want to answer. Okay, half times, or maybe I didn't know that I wanted you to answer. So half times L to the 1/2, L being positive, the square root of a positive number is positive, divided by another positive number, K to the 1/2, the square root of a positive number is positive. So we have a positive slope. So in fact, output is increasing in K, no matter what the values of L or K, as we expected when we looked at this function to begin with. Okay, but now we want to know, is it increasing in K at an increasing or a decreasing rate? This is the function that tells me the slope. I can look at this and say, is this function increasing or decreasing as I increase K? And well, there's two ways of answering that. One, I can say, let's take the derivative of it, see if this function, which tells me the slope, does the slope itself has a positive or negative slope? Yeah, I don't even have to take the derivative of it in this case, however, because I can look at this and I see, if I increase K, this is going to get smaller because K is in the denominator. If I increase K, I'm increasing K to the 1/2. So the denominator gets larger, so it gets smaller. So here we do see that the slope is decreasing, and we see, which is going to be embodying decreasing returns to, it's going to be embodying decreasing marginal productivity of K. Okay? So when I have K to the 1/2, and in fact we could go back and see this, we could say, all right, yeah, I do know that the square root function increases at a decreasing rate. If I wanted to take the second derivative, say what is the slope of this slope, well, I'll go back to the other expression for it and use my rule again. 1/2 L to the 1/2, K to the negative 1/2, okay? So I use my expression, so this is all a constant, and I can take the derivative of this term. I remember my rule. I take this negative 1/2, put it out front, so I say negative 1/2 times this constant that we just said was a constant, 1/2 L to the 1/2. Okay, and then what do I do with this guy? This K to the negative 1/2. Well, I have to subtract 1 from that. So I subtract 1 from the exponent. So I say K to the negative 3/2. Okay, and I see this is negative, right? A negative term, negative 1/2, times a positive term, 1/2 L to the 1/2, times another positive term, K to the negative 3/2. Okay, this is just 1 over K to the 3/2, which is obviously positive. Okay, so yeah, we see sort of two ways of getting the second step. You can shut up there.